Let's get it. Okay, so the next section here is talking about which I just wrote here, surface area. In general, we're talking about the area of a surface revolution, right? So we did volumes of revolution in chapter 5, but now we're doing surfaces. So just kind of covering the right. So if I have an object like this and I revolve it around, my x-axis here, right? I don't care as much about what the space is that's occupied in between. I more care about like what's being wrapped around it, like how much area is around the shape. Okay, so to start this one out, again, we want to kind of start with a little bit of discussion. And so the book kind of gets into first introducing this concept of like kind of find the surface area of simple shapes, right? And the way that we do that is it kind of gets into talking about a cylinder and kind of stretching that out and how we find the area, right? So maybe I'll make that out first. So if I have a cylinder, right? And I want to find the surface area of this cylinder. I want to find how much air like around that this covers, like how far it goes, right? I kind of stretch it out. Essentially, I'm wrapped, right? So I take the cylinder, I kind of take the outside of it, and I stretch it out, right? So let's say that the radius is r, right? It's like r, and then the height of my cylinder is going to be h in this case, right? If I take the cylinder again and I just kind of stretch it out, right? This length is going to maintain. It's just going to be h. What do we think, right? So again, I'm going to like maybe take this part off, just rip this whole part open, and just pull the cylinder apart, right? So any guesses on how long this portion is going to be, right? So if my radius is r, it's 2 pi r. Good. Yep, absolutely. So the length of this section is going to be 2 pi r. I did your r squared. That's going to be like the area of the circle, but we just want the circumference in this case. So the length of that side is going to be 2 pi r, right? And then the length of this side is going to be h. Okay. Now, what's going to happen here? If I take essentially it takes. We're going to look at a cone now. And the reason being is because I want to, right, again, if I'm wanting to look at the surface area, I care a little bit more about trying to fit close to the curve, right? So kind of getting as close as possible to, kind of like with trapezoid rule, how we would say, okay, well, I want to have this edge get close and this side get close enough to get the area from it. And so the book ends up defining it again. I'll just kind of skip over some of the intermediate kind of setting this up. Is using some of the logic here to put it all together. I can define that the surface area of this cone, if I sort of stretch it out, is going to be pi times r times L. Okay, where r is going to be the radius of the circle, and the length here is going to be the length of the top and bottom of this cone. Okay, and so we cut it, we stretch it apart. Again, if you want to see that, we cut it, stretch it open. I'm going to get something that looks like this. And so the radius is this much, right? And theta, right? But if I pull it apart, the length here is going to be the same as the length up here, which is going to be 2 pi r, right? And so to find the area of this thing, right, again, it's going to be L, we take, right, who remembers the area of a sector? Right, if I have, so again, what I mean by that is if I give you some angle here, and then it's a radius r, and I want to figure out what the area is of this section. Anybody remember what that formula is going to be? Close. You're thinking of what the arc length is, where you take the radius times the theta. But I'm not as interested in the arc length in this case. I want to know what the area is going to be. That formula, if you remember, is 1/2 r squared theta. Okay, you might remember this from trade. It would have hopefully covered that at some point, but that's what we get. And so applying that here, right? My angle, which we may not know exactly, it's going to be 2 pi. Let's see. Well, actually, this is we know the arc length of this from this formula, right? Which is going to be 2 pi r times 2 pi. Sorry. It's 2 pi. Theta is going to be, oh, well, okay, so the radius, this should be, if you want to read it, you can. I don't want to get on that too much. But the area here we're going to find is pi r IRL. Okay, and that's like for a basic cone, right? That's going to be the surface area. That's, we want to use that basic shape of the cone to get everything else. Okay, so then the book goes a bit further and it says, well, what if I'm dealing with like where I have the cone shape, but I'm not getting, I don't want all the cone, I only want like a portion of it. Okay, so I only want this bottom half, for example, and I want to figure out what the surface area of this thing is going to be. Well, in this case, right, if I want to kind of figure out what the area of this is going to be, I have 2 cones, right? So if I want to find, so I can call I would call like this L1 and L of some sort. And so if I want to find the length of this portion, I can just take the 2 of them and subtract the pieces, just figuring out how my radii are related to each other. But in the end, even though it would look kind of odd in this case, again, we're just basing off this L here. The area of this is going to be equal to the surface area is 2 pi r. Okay. Again, this r is based on, well, it's actually, if this is R1 and this is R2, then the R here is sort of the average in this case, kind of the one in between. Okay. So all that being said, we kind of take our shapes, we want to use our building blocks, and using a bit of geometry, we can kind of pull this out. Okay, so this part isn't as important. We'll just go ahead and move on to putting this into our integral, but this is what we're working from. Okay, so essentially, what we're saying is when we're talking about surface area, is I want to take to approximate the section I'm working with, I'm going to take the circumference of the region, right? I'm going to take the circumference of this area here, this section, and then I'm going to multiply that by maybe the length of the ring that of whatever ring section I want, right? So again, maybe I'll draw a bigger one just to demonstrate here. Draw a bigger ring. Here we go. So this length Maybe I'll draw it in green so you can see it. Okay, so I would find the circumference of this section of kind of the average circumference of the ring, which this would be pretty close. So we would just say 2 pi r, right? Kind of r, some r in between, the bigger one and the smaller one. Again, we're going to be doing this on an infinite scale, and so they're going to kind of be pressed into each other. And then we're going to multiply that by the length of the side, kind of like what we multiply the length of the side here. And that's going to give us one piece of this area, right? So ultimately then, right, I want to find the total of adding up all those different rings and see what I get, right? So to get our surface area, this is going to be the sum, again, from I equals 1 to n. And so we're going to have 2 pi, right, times the radius at that point, which I'll just go ahead and put r for now. And then we want to do L, right? Now L in this case, though, is the same L that we were working with in 8.1, right? It's the same, I pick 2 points on the curve, and I find the line segment between them, right? And so this is going to be, again, it's going to be pi minus 1 pi. Okay, so we're going to take 2 pi, and then maybe I'll call this Ri for now, kind of the radius of that particular ring, of 2 pi Ri times the length of the line segment at that point. Okay, so I pick some specific radius, and I have my 2 points that I go in between. Okay, but we know what this is, right? We worked this out. This is going to be, we're going to have 2 pi Ri, and then this is going to be the square root of 1 plus f prime of xi star squared, and then this is going to be delta x, right? And then with this, right, I have everything I need, right? I guess I should say this is approximately, and we want it to actually be able to limit this, right? So then I have everything I need here to be able to write this as an integral because I have my delta x and I kind of have an xi, except that I still have this Ri here term that I'm dealing with, right? Well, let's think about what our radius is, right? So if I'm, and again, these are going to press together, so we don't need to worry about, oh, what's the average, and where am I going to be at? The radius, right, is always going to be measured from the x-axis, right, or depending if we're revolving around this way, the y-axis. I'm going to measure from the axis up to the curve, right? But what is this distance? Do we know what this distance is? It's f of x, right? This is our function, right? The distance from the axis up, that's f of x. And maybe in that case, it'd be f of xi star, right? The same way. So my Ri is my f of xi star. It's my same function, right? Times the square root of 1 plus f prime of xi star squared delta x. But having this now, I can more clearly see, okay, this is a function of my x, this is a function of x, and there's my delta x. I can write this as an integral, which is going to go from a to b of 2 pi f of x times the square root of 1 plus f prime of x squared dx. So we're left with this square. Okay, so the only difference really from the arc length formula to the surface area formula is that we take that arc length, right? Which again, if you wanted to, you could recognize this as ds, kind of we talked about at the end. I just take 2 pi f of x times that ds part, that arc length, and that's going to give me my surface area, right? Which on an infinitely small scale, this is going to give me exactly what I want, right? Again, here, there's kind of a bit of a, maybe a shakiness in terms of, well, I take the average in between, we'll use that to represent the area. We'll have that as like our cylinder, you know, that we go from there. But here it's tight, like this is gonna work out, this is gonna give us exactly what we want. Okay, so good. I think that's everything I need to say on that for so far. So any questions at the moment? If you have any, please let me know.
Area of the sector, theta degrees over 360.
Well, you can, but I mean, this formula is for radians, right? If you decided to, I mean, it just depends on what, I guess, where you're coming from, right? I mean, you could technically rewrite this in a way where you could have theta over 360 plug in angles, but we'd rather use radians instead. We don't want to come from a place where we're taking degrees and then put it into a formula, right? Because obviously, like, our work only really makes sense if we're dealing with kind of our pi values, getting like pieces of a circle, right? I wouldn't go to this formula and be like, oh, I'm going to put 90 degrees in, right? I'm going to put pi over 2 in instead. They mean the same thing in terms of trigonometry, but whenever you're graphing them, right? We represent our sine graph, for example, as right. Let's do a little portion of it. We have 0 here and pi over 2, pi, 3 pi over 2, and 2 pi here, right? I wouldn't want to make this graph, right, or make my work in a way where instead of those, I have this is 90 and 180. Like you're not going to want to stretch out your function in a way that it goes so far out, right? So the radian degrees. Okay, and again, some of the stuff is a nice review over, but of course, for our sake, we don't need to work through it, but I do want to at least kind of the basis of, okay, well, I have, this is kind of an approximate, you know, unfurling it to find the area of that's going to be my shape. Taking an average here, I can get it an approximate area in terms of this L, and maybe it's this R between. Again, you can feel free to read through if you want to. It's all about getting approximates, right? Because again, when we make it infinitely small, it doesn't matter if you have like the average, right? Because if I have, right, as I take these 2 points, right, and I move them together, right, on my curve, it's all going to be here. So the average of that one point is just the 1 point, right? It just stays where it's at. So our work towards infinity kind of cleans up. Okay. Any other questions on that front? Okay. Before we use this formula, I need to make some maybe distinctions here, because this is going to be different whether you're revolving around the x-axis or the y-axis, right? Because if I'm revolving around the y-axis, for example, I have y equals f of x, my function isn't, I'm not going to use f of x as my radius anymore, right? Because that's not what my radius is going to be, right? I can't, right? Again, I'll roll it real fast. And it rotates around, and I get this. Right? My radius is this distance, right? It's not f of x, which is going to be this distance, right? So I need to be careful when I'm working with these problems to know what exactly I plug in, okay? So we're going to kind of label those here, okay? So if I go about the x-axis. Then, in the easy case, where I just have a function of x and it's going about the x-axis, I just use that formula. So my surface area, so, and maybe I'll label y equals x. And my surface area is going to be the integral from a to b, 2 pi, and then times f of x. And maybe, well, actually, I'll put it, y equals f of x, right? So I'll just write y here. Times the square root of 1 plus f prime of x squared. So I get this. Okay, so that's my surface area. I gave you can write y as f of x, but there's a specific reason why I'm writing it that way. What happens if I have x as a function of y, but I still want to revolve around the x-axis? So let's talk through it real fast, okay? So here's my curve, right? And we're going to revolve it, and this function is actually f of y, right? So instead of it being y equals f of x, it's in terms of y, right? My length, right, just like with the arc length, won't really change much, except that I take the derivative of the y function instead of, like, I just take the derivative of f of y and dy, right? But we need to be careful about a radius, right? You're not gonna put f of y here and then plug this in, right? Because f of y, that's my x distance, right? Which tells me this, and how far I go this direction. But that's not my radius around the, like, going around the x-axis, right? That's this, right? That's this distance here. Maybe I'll kind of match them up. I want the green radius, right? So again, I don't want this distance because this distance is x, but I want this distance. What is that green distance going to be? Still y, yeah. Y, that's my y distance, right? That's the y distance up to the graph, right? That's how far in the y direction I go up. So if I have x equals f of y, of course you're going to change, your bounds are going to be in terms of y now, right? Just depending on what the function is. But you still do 2 pi y times the square root of 1 plus f prime of y squared dy. Okay. These ones are actually really nice because you don't have to plug in the function. You just simply have y there, right? So this opens up a lot more possibilities for the f prime because you can do like a u sub potentially to capture that y and bring it in there, and it works out nicely. But again, I wrote y in both cases because it is y in both cases, right? If you're going about the x-axis, that better be a y there. In this one, I do have to plug in whatever the function is here, but in this case, I don't. Okay, does that make sense? Does that distinction make sense? So again, we'll do examples. But if I'm going about the x-axis, I should always put y here. I might just have to plug in one time that I do. Okay. Now the y-axis is the same sort of story. So if I have y equals f of x, then, so let's think about this case, right? So in this first case, the distance that I was looking at, that r, the radius distance was my y, right? It was the y distance. So, but we don't want the y distance in this case now, right? We want the x distance. So, right, because I want the distance left to right. I don't want the up and down distance, I want the left to right. So, we're going to have the integral from a to b of 2 pi x. That's the square root of 1 plus f prime of x squared. x. And the surface area here is going to be a to the b of 2 pi x times the square root of 1 plus prime y. Okay, and that's all there is to it, right? If you have y equals f of x, right, or x is f of y, you're going to set up this piece as you would the arc length. But the only thing that changes is if I go about the x-axis, I need to have y's here. And if I go about the y-axis, I need to have x. Okay, because that's a radius. Okay. Any questions on these formulas? Any at all? Nope. Okay. Cool. Well, let's do some examples then. So just like last time, we'll like set up one first, and then after we'll do over. Okay. So we'll set up. So we'll do. Sure. Why? Okay. Well, let's start with. Yeah, we'll do numbers. Okay. So we'll set up. Line surface area by rotating about. And we're going to do this two ways. First way is about the x-axis. And the problem in this case is going to be y equals the negative second power, and we're going between 1. Okay, so we're going to set these up, right? So they always start out the same way, right? So let's start out with, we'll start with the x-axis, right? So I want to take the surface area. It's going to be equal to the integral. Okay. The integral from what? From what to what? One to two. Thank you. Yeah. 1 to 2. Okay. And we're going about the x-axis, right? So do I put y here or do I put x? We put y, right? If I go about the x-axis, I have to put y, and if I go about the y-axis, I have to put x. It's the opposite of what you think, right? Or like what? It's the opposite of whatever the axis is, right? So we take 2 pi y, and then the square root of 1 plus f prime of. Now I have y equals x, right? So I want to do f prime of x squared dx, okay? So I'll plug in from here. This is how we're going to start this, okay? So we're going to do 1 to 2 of 2 pi. Now what's y in this case? We do x to the negative second power. Yeah. Square root of 1 plus. What's x to the negative second power? Yes, negative 2 or third, right? Yeah, I meant to ask what the derivative of x to the negative second power is, but yes. So it's going to be negative 2, right? And we can do x to the negative third or negative 2 over x to the third power squared. Yes. Okay, and then you would attempt to work this out to find an answer. In general, right? But this one we're just setting up because it probably may not work in this case, but that would be my integral. Right? So again, I have to keep track of two things. I have to say, is it a function of x or is it a function of y? And what axis am I flipping around? Right? We have a function of x in this case, so that's what's going to go here. And since we're going to go the x-axis, I need to go y. Okay. So let's do the second one real fast. So surface area is, so now we're going about the y-axis, right? So what are my bounds gonna be in this case? What's my bounds gonna be in this case? 1, 2. Yep, that doesn't change. 2 pi. But you're right here. This, we're going about the y-axis now, so now I need to do x. Okay? Because I'm going about the y-axis now. Times the square root of 1 plus. Now from here, this part stays the same, right? So it's still going to be f prime of x squared dx, but now I'm going to put, so I'm just going to write that in there still. So that's going to be my only difference. Okay, so I just write x. Okay, now do I plug in? Is there a function that I put in for x? There's not going to be, right? Because it's y equals f of x, so I can just leave x, right? So I just leave x there and I can work it out like this. Okay, and that'll be my integral. Okay, so about the x-axis, I had to put in y, which was actually negative second power in this case, and then to go about the y-axis, I just put x instead, and just x. Okay, does that make sense? Good. Aaron, questions? I want to erase this part if you have questions. I have the answer. Okay, so now we'll do number, let's see. We're going to find the exact one now. And so to do this, we'll start with number 8. Okay, and number 8 says that we are going to take y equals 5 minus x, and we are going to go from between 3. Okay, so I want to find the surface area of this curve between 3 and 5. Okay, and we want to do this about the x. Okay, so right, we're going to use our equation, right, to set this up. So surface area is going to be the integral from what to what? 2 pi, what goes here? 2 pi times what? Y. Okay. Because we are going about the x-axis, times the square root of 1 plus f prime of x squared. So first, let's try to figure out what the derivative of 5 minus x is going to be. Okay. How do I find the derivative of 5 minus x? So, sorry, square root of 5 minus x. How do I start it? Yeah, so we need to use chain rule, right? Yep. So we're going to have, and I can think about this as 5 minus x to the 1/2. Good. So I'm going to have 1/2 times 5 minus x to what power? -1/2. Times what? Good. So I get -1/2 essentially. So I'm going to take that and plug it in. So I'm going to get the integral from 3 to 5 of 2 pi times right, because that's y, times the square root of 1 plus, and so I'm going to write this as 1 over -1 over 2 times the square root of 5 minus x squared dx. Okay, good. So let's square the inside real fast here. So we're going to get the integral from 3 to 5 of 2 pi times the square root of 5. Oops, sorry. Square root of 5 minus x times the square root of 1 plus. What do I get when I square this thing? Now, this looks like it still might be a little odd, but we can actually simplify this a lot, right? Because, can I take this and multiply it inside? They're both square roots, right? This is a square root and this is a square root, so I can just multiply the insides together. So I'm gonna get the integral from 3 to 5 of 2 pi times, okay, so we get 5 minus x times 1, which is 5 minus x. What's gonna happen when I multiply the 5 minus x here? 1/4. Because it just cancels out the other 5 minus x. That's all. Okay, which this is an integral I can do. I might have to do a little bit of use of, but I can absolutely do it. And maybe I'll go ahead and take out that 2 pi as well, because it's a constant. You can't always, by the way, in each case where there's 2 pi, you can kind of just pull it to the outside. It doesn't have to stay in there. It is a constant, so it's not a big deal if you take it out. So we'll have 3 to 5 of the square root. Now what's 5 plus 1/4? Okay. How do I take this integral? Okay, what's u gonna be? So the u is gonna be what? Which I'll just go ahead and throw on the other side, which will leave us with negative 2 pi. Again, that negative is goes to the du. And then maybe we'll go ahead and change our balance as well, since we'll have to do that. So if I put 3 inside of my u, I get 21/4 minus 3, right? So maybe I'll write that out. So we get 21/4 minus 3. How do I do 21/4 minus 3? So 21 minus 12 is going to be 9. So we get 9/4. Good. And 5 is going to be 21/4 minus 5, which you do something similar, and this one actually just leaves us with a 1. So we get, okay, so negative 2 pi integral from 1/4 to 9/4 of the square root of u, or maybe I'll write that as u to the 1/2. Okay. How do I integrate u to the 1/2? What is it? Power rule. Good. So what do I get when I do power rule? Right, we're going to get u to the 1/2 plus 1, which is 3/2, over 3/2, or I could multiply that as 2/3. And then I evaluate this from 1/4. This all constant stuff will just kind of hang out the outside for now, so we get negative 4 pi over 3. And then that's times, we'll have 1/4 to the 3/2 minus 9/4. Okay. How do I do 1/4 to the 3/2 power? So what's the square root of 1/4? 1/2. And what's 1/2 cubed? 3, 1/8. Okay, now let's do something similar to 9/4 here. So square root of 9/4, 3/2. Okay, and then we just need to take 3/2 plus 3/2. So we get 1/8 minus 27/8. So 1 minus 27. So you get negative 4 pi over 3 times negative 26 over 8, which you can simplify that, but there's a lot of ways you could simplify this. First, our signs are going to cancel each other. 4 over 8 is the same thing as 1 over 2. 26 divided by 2 is 13. So we're just left with 13. So, again, not necessarily difficult in terms of plugging in, but might just take a bit of work, okay? If I were to do this integral, but instead to rotate about the y-axis, what would be different? You'd have x here instead, right? So I would just leave x and I wouldn't put the square root of 5 minus x in, and then I couldn't do all that multiplying, so I might have to find some other way, which I'm not actually sure if that one would work out, but that would be how we would approach that. Okay? Good. I want to try to do at least one other example. Like, let's see. Let's take. We'll do, I don't know, let's make this a little more, try to make things a little bit more interesting. Okay, so I want to jump to number 16 now. Which is going to be x to the 2/3 plus y to the 2/3. 1. And we have 0, so that's going to go to y, so that's going to go 1. And we're going to go about so I want to find the surface area of this curve from 0 to 1 by rotating it around about the y-axis. Okay, what's different about this one than what we've seen already today? Right. Yeah, exactly. A lot of what people have been saying is true about what we're given and kind of how we approach it. The big thing is that this function is not explicitly in terms of one or the other, right? You have x and y on the same side. You don't have x equals something, you don't have y equals something, right? But we are given bounds, right? So we have an idea of where we want to go, right? Of which one we should solve for, right? So what do we think? If I'm given my y bounds, right? What should I solve this for? What do we think? Right, so our integral is going to be in terms of y, which means we need to solve for x. So I'm going to take this thing, I have x to the 2/3, and I'm going to subtract y to the 2/3. Sometimes you just need to do this as your first step of the problem, is to solve it for one of the variables, which we'll do here, okay? And then if I want to get x by itself here, I want to get rid of that exponent, what do I do to both sides? As power. Right? Because remember, whenever I have something to an exponent, if I raise it to another exponent, I just multiply the exponents together. And so I want 2/3 times something to be 1, which would be 3/2. So I'm going to get x equals 1 minus y, 2/3, and then all of that to the 3/2 power. And so this is going to be my function, okay? That I'm going to use for my integral. Right, so we're going to have, right, so someone help me write this out, right? So we have the surface area, integral is going to be from 1 to what? 0 to 1 of 2 pi, okay, it's going to be here, x, good. Right, which we have, which we're going to plug in, and then we want the square root of 1 plus, what's going to go is this gonna be f prime of x, f prime of y, what is it? F prime of y. Okay, so, exactly, we have x, so I'm gonna take that, I'm gonna plug it in. Okay, and then this is gonna be 3/2, right, because that's what x is, times the square root of 1 plus. So let's take the derivative of this real fast. Right, so let's get y. So what is, how do I find f prime of y? Chain rule, good. So. Mhm. Good. Good. The negative 1/3. So a little bit interesting things happen there, you know, with all the, with their different powers and stuff, but we would hope that, yeah, that's about. But this is our derivative, right? And so this is exactly what I'm gonna take and plug in here, which is gonna be, so notice this 3/2 and this 2/3 are gonna cancel each other, which is nice. So I'm gonna have negative y to the negative 1/3, and then times 1 minus y to the 2/3. Raised to the 1/2, or maybe I can write that as the square root. Squared. Like that. And then dy, of course, we're gonna get that. Okay, we're gonna get 0 to 1 of 2 pi, 1 minus y to the 2/3, raised to the 3/2, times 1 plus, okay. The negative is gonna go away, and then the square root is gonna go away. I'm gonna be left with y to the negative 1/3, or sorry, with negative 2/3, because we have the square of that as well, right? Negative 1/3, y to the negative 1/3 squared is y to the negative 2/3. What's gonna happen when I take that times this y to the 2/3? Right? So let's, again, maybe I'll write this separately. So when I square this, that negative goes away and I get y to the negative 2/3, right? Because that gets squared, times 1 minus y to the 2/3, because that square root goes away. So what's going to happen when I multiply this times this? Yeah, good. Y to the negative 2/3 minus 1. Okay, which, notice, is going to cancel each other. Right, so we get y to the negative 2/3. 0, 1, 2 pi. What is the square root of y to the negative 2/3 power? Okay, does that, yeah, that's y to the negative 1/3. Does that make sense? Right, if I have y to the negative 2/3 power, and I raise it, I square root, right, or take it to the 1/2 power, I just take negative 2/3 times 1/2. So I get, and maybe I'll write that up front here, times 1 minus y to the 2/3. Let's see. So from here, to do this, you would, right, what would we want to do? Solve this. What ideas do we have, right? So I have 2 pi, which can just go to the outside, and then I have y to the negative 1/3, 1 minus y to the 2/3, that's the 3/2 power. So what would be a good step to try to integrate this? Right? Let's go back to chapter 7 real fast. What should I try? So let's think, right? Can I simplify this? Can I simplify this down at all? Yeah, I wouldn't multiply it. Yeah, it wouldn't really help us much in this case. So you could, yeah, so we could try to take that cubed and then multiply it out. But again, there's still a conflict between this negative 1/3 and 2 here. So maybe we could try a u sub. Right? That would be the next, is there a simple substitution? So what happens if I let u be 1 minus y to the 2/3 power? Right? Didn't we do this already? Well, yes, we did. It's over there, right? when I took the derivative of y to the 2/3 power, it was negative 2/3 y to the negative 1/3 power, right? Well, we have y to the negative 1/3. Do we not? Good. So that's, I'll go ahead and I was contemplating like just kind of this one, maybe. We don't want all of our situations to be so to be too easy, right? We have something a little more interesting, right? So u is this du is going to be negative 2/3 y to the negative 1/3, which I'll go ahead and I'm going to multiply this negative 2/3 or divide or multiply by its reciprocal. Get negative 3/2 du y to the negative 1/3 dy. So then I'm going to get, and maybe let's go ahead and we can try to rewrite our balance as well, right? If I take 0 and I plug it into my u, what do I get? 1. If I take 1 and I plug it into my u, what do I get? 0. So that one's actually perfect. And then I'll go ahead and I'm going to take negative 3/2 times 2 pi, which is 2 pi. And so we have u to the, okay. How do I integrate u to the 3/2? Powerful. So we're going to have u to the 4 by so 2/5. Yep. Negative 6 pi over 5. Yep. I was like, wait a second. That negative 6 pi over 5, u to the 5/2, and then we just go from 1 to 0, which that's a lot easier than the other one was, right? Because we can, there's not as much work involved because 0 to the 5/2 is 0, and 1 to the 5/2 is 1. But when we do that subtraction, there's going to be a negative sign that comes out, so we're just left with. Okay, so interesting enough, that just ends up being 6 pi. Okay, now, and this is a good example to study. Don't on the mandatory homework, I think the first one is like the first example we did, which was number 8, I think. The second one is a lot more, is a lot easier to use. I will tell you that. So don't fret too much about it. Yeah, and maybe I'll just ask real quick. If I was taking this problem about the x-axis instead, what would change? Well, we wouldn't want to solve for a different one because yeah, good. We wouldn't want to solve for a different one because we already given the bounds, but we would just put y here instead of x. Okay, and that makes the integral a lot easier, right? And maybe just to, again, I don't need to completely. Let me see if there's a quick example that they do. I won't work all the way through this one, just to kind of show you. Right, so on number 14, for example, they have an x equals y squared, right? And we're going from 1 and 2, right? And this one's about the x-axis. Right, so to set this one up, right, we're going to have the surface area that's going to be the integral from, what are my bounds? 1 to 2, yeah, thank you, of 2 pi, what goes here? 2 pi y, good, and square root of 1 plus, so what goes in here? F prime of y. We can find that easily though. What's that prime of y? 4y. Good. And then dy here, right? Which is going to give us the interval from 1 to 2 of to plug anything into this Y. No, because we're in terms of Y, so that's okay. You would just do this integral at this point, okay? So again, I just wanted to show that real fast so you know you don't always have to plug in something for this. If you have the right variable to match, just leave it. If you had a function of X here that you want this, you need to change that as well, but in this case, just leave it. And then from here, it's really easy to use it. Okay? So that's what. Okay. If you have any other questions, we're done a bit early, so I could. Tomorrow, my goal is, I want to try to read that as soon as possible. That's my. Yeah, you too. Thank you. Yeah, you too. Thank you.